Okay, on number 12, we have a colony of bacteria. It's grown under ideal conditions in the lab so that the population increases exponentially with time. And it says at the end of the 3-hour period, there's 10,000 bacteria. At the end of 5 hours, there are 40,000 bacteria. So ultimately, how many bacteria were initially present? So ultimately, we need to make sure that we use the correct model here. And if it's any kind of exponential growth situation like this, then our model is just going to be the general model, which is a times b to the x. So it's a model that we've been using since algebra for exponentials. A, of course, remember, is the initial condition, and b is either the growth or decay rate. And in our case, we know that there's 10,000 bacteria present, and the time frame on that is what? 3 hours. So we'd ultimately get that, which is nice, except for we have 2 variables there. True. They don't tell us what the growth rate is or anything, but they also give us information about the fact that there's 40,000 bacteria after 5 hours. True. And so the question is, since we have 2 equations that have 2 variables, shouldn't we be able to use substitution and solve this, or elimination? One of the 2. So let's just say, for argument's sake, that I solved the first one for A. And if I do that, I could plug that into my other equation, and I'd have 40,000 equals 10,000 over b cubed times b to the 5th. So I'm going to replace the a with what a is equal to, and with that I'm going to have 40,000. 10,000 b squared would be my new equation. And if I divide, I'm going to get 4 equals b squared, and ultimately what does b equal then? 2. You don't want to add, obviously when we square root something, plus and minus is an option here, but in this case the base of an exponential equation is always going to be positive, so we'd have just the primary square root. Alright, and again that is our general equation so far would be that now, but ultimately we need to know what is a. Well, we know the relationship between a and b is right here, so if we plug in our 2 into this equation, 2 cubed is 8, so what's 1,000 divided by, or 10,000 that is, divided by 8? 10,000 divided by 8 would be 1,250. And so that means our final equation then is going to be 1,250 times 2 to the x. And keeping in mind though that that would be the actual equation for this particular experiment, except for they didn't really ask us for the equation, they just asked us for how many we had at the beginning. So remember, at time 0, the reason 1,250 is the answer is because at time 0, what would this do? If I go 2 to the 0, that would give me 1, and we get our answer for the number of bacteria, but y would equal 1,250. So there would be 1,250 bacteria present at the beginning of the experiment. Questions on that one?
Once you get the where it says a equals 10,000 divided by 8, I don't know where you got the 8 from. Is it b to the third? B to the third? No, over. Down.
Yep.
Equals 2. Right. On the screen.
This?
After you put in the 2, you have the after you put in the 2 into the equation, you have the 10,000.
On this side?
Yeah, this side. Yeah.
So
I don't get where you get the 8 from.
because ultimately the b that we found was 2, right? And so if I put it into this equation, that's 2 cubed, which is
that
8. Alright, good question. What else? Anything on this one before we move on? Next one? Cody? On 9 it says find the amount of time required to make a 2,000 investment double if the interest rate is compounded annually, monthly, quarterly, continuously, and so on. So ultimately our general formula that I gave you was the following, and this would be for compounding. So we want the money to double, so in other words we want it to go from 1 unit to 2 units, so whatever that number is, we can just use 1 and 2. We want it to double from $1 to $2, or divided 1,000 to 2,000, we'd ultimately divide by 1,000 and have 1 and 2 in those positions regardless of how much we start with. And our rate here is 0.0475, compounding annually would just be 1, and then we'd have 1 times t here, and ultimately the t is what we're after here. We want to know how long it's going to take to go from 1 unit to 2 units. So the solving part here is just going to be 2 and then 1.0475 to the t. And if we do the natural log of both sides, we could bring the t out in front. And so if we do the division, natural log of 2 divided by natural log of 1.0475. And if we calculate that, what do we get for time? Natural log of 2 divided by natural log of 1.0475. Not spend all day sitting around waiting for somebody else to do it. How much?
14.936.
Alright, so we'll take that much if our compounded yearly, which again, M stands for how many times we compound per year in the equation. If we were to redo that and do 1 plus 0.0475, and the next one for part B we had to do it, which was monthly. Monthly we'd have a 12 here, and this would be 12t up here. And once again, we would still do exactly the same thing. We would take the natural log of both sides, solve for t. Should take less time than this, right? Turns out not much less, but ultimately this would be our part B. Once you finish that one, and then part C, we're going to do the same thing, but it's quarterly, which means that quarterly this number would be 4. We're doing it 4 times per year. And then finally part D, it says continuously, and if it's continuously, then we use our y equals, we can actually call it a, just like we did these other ones. We'll use a equals p times e to the rt. And so our amount is double e to the 0.0475 t. And if we take the natural log of both sides and solve for t there, we should get something that, again, is a little bit less than all the other ones that we did, 'cause it's going to take a little bit less time if it's compounded continuously. So again, it's just a matter of doing the algebra on that, solving it for t, and good to go. What else? Anything else from our 6-4 assignments? Justin?
18.
Yeah, in 18 we got it's like a Newton's law of cooling problem, and as I mentioned, the Newton's law of cooling, all we need to be able to do is know the formula, and actually that's T, right? And so if we know the formula for Newton's law of cooling, again, we don't need to know how to derive the formula. You know what? I got that backwards. That's the S. That's the 0. And that's the S. There we go. Okay. So again, that T, the first T is just temperature. T sub S is the surrounding temperature. T sub 0 is the initial temperature. T sub S is the surrounding temperature again. And then e to the kt. Keep in mind it's negative k because it's cooling, not getting hotter, if you will. So knowing that, then if we can see what we got here with the number 18, tells us we got an aluminum beam was brought in from the outside cold into a machine shop with the temperature is held at 65 degrees. Ultimately, just based on that one, what do we know so far then? That would be T sub what? Remember, the temperature in the shop is held at 65 degrees. Wouldn't that be the surrounding temperature? Okay. So that right there would be my 65 would go there, and 65 would go there. Okay, we know that for sure. All right. And then it says after 10 minutes, the beam warmed to 35 degrees. So keep that in mind. So after 10 minutes, it warmed to 35 degrees. We're looking for the initial temperature, keep in mind. So we don't know the T sub 0. That's what we're after here. Right? We know that that the beam became 35 after a certain amount of minutes, which was how many? 10 minutes. All right. So ultimately, we know that all that stuff. Okay. What the problem that we have with this equation though is what do we have? Why can't we solve it? It's got 2 variables in it. So if it's got 2 variables in it, that's obviously a problem. Okay. However, they gave us more information. They told us that after another 10 minutes, that the temperature was 50. So that means it went to 50. Still don't know the initial. Okay. And I'm not going to fill in that blank quite yet because I want to think about how we want to do this. Let's think about this. Okay. Keeping in mind that it says after another 10 minutes, okay, it got to 50 degrees. True? So that means if I were to put 10 minutes in there into that sentence, okay, wouldn't I then know this? Wouldn't this be 35? Because we know after the first 10 minutes it's now 35 degrees, right? And after another 10 minutes it gets to what? It gets to 50. So with that, what would be nice is with that part is I can now calculate what? I can calculate K. And if I calculate K, I can use my K here, and I can use that to find T sub 0, can't I? So let's calculate K. So we got negative 15 here, we got negative 30 here, got e to the negative 10K. And we're solving an exponential equation. Make sure you get the e, or whatever, exponential base is alone first. So dividing, we get a half over here, e to the negative 10K. Questions so far?
I have a question. How did you find T sub 0?
I didn't yet.
You put in
Oh,
35.
this one. Because again, they told us after 10 minutes the temperature of the beam is 35. Okay. And so 10 more minutes it goes from 35 to 50. Right? Is that after the 10 minutes, but now we know the temperature is 35. So if we use that as the initial temperature, it goes from 30 to 55 in 10 minutes. Okay. So we can use this 35 that they told us as the initial temperature for that second half of the experiment, if you will. Okay. So if we use that as our T sub 0, we can do natural log of both sides now. We get negative 10K. And if we do that, we're going to negative log of half divided by negative 10 equals K. And I'm going to leave that as is because we don't want to get a rounded answer for that and use it to solve our other sentence. Alright, so now what that allows me to do is go back up to the original here, which is this one, and plug in my K here. So let's see what we get. We got 35 minus 65, T sub 0 minus 65, e to the negative, and in here we're going to have negative natural log of a half over negative 10 times 10, if you will. We, again, coming from this one right here, this is the original one that we wanted to solve. That has T sub 0 and K, but now that we know K, we can plug our K into it. And let's do the math here. So ultimately, the negative here is going to make it positive. True? And we got 10 here and 10 here, the 10 on here and the 10 on here are going to cancel out. And then we're going to be left with e to the natural log of a half. So isn't that just a half? And over here we got negative 30 on this side. And if we multiply by 2, we're going to do negative 60 equals T sub 0 minus 65. So multiply by 2 both sides. And if we add 65, we get 5 degrees is our T sub 0. And it's degrees Fahrenheit. And does it make common sense to be 5? Should be less than 35, right? Then again, to check this, could we go back to our original here? Just for argument's sake, just if we go back to our original and we put in our 5 here for our initial temperature, and we put in the K we found, okay? It should be true that this side and this side are equal, shouldn't it?
Yeah.
Okay. So again, calculator problem, pretty easy to check too. Alright, so therefore our initial temperature would be 5 degrees Fahrenheit in this case. Questions on any part of that one? What else?
27.
And 27, we have another differential equation given here. We got dpdh equals kp. And you'll notice that it is of the same form of the original one that we looked at in our notes, which is ultimately dy dx equals ky. And so we know that this type of differential equation gives us an equation that is of the same form every time. So we learned that in our notes that dy dx equals ky would lead us to y equals y sub 0 e to the kt, which ultimately would be our exponential change model. We went through the derivation of that, but just to re-illustrate here, if we did our separation of variables part here, okay, so if we didn't remember that, we could separate variables. We get natural log of absolute value of p over here, we get kh plus c over here. And then if we compose both sides with e, we get e to the ln of absolute value of p, e to the kh plus c, that is. And over here we get p, over here we get e to the kh e to the c, keeping in mind that e to the c is just a constant. So we get p equals c times e to the kh. Okay. And actually I should have a kx up high on that one. Usually we use dy dt, I guess, but again, the variables don't necessarily matter. And keep in mind that the c right here, if I were to put h equals 0 in there, I'd be left with c. Okay, that c, again, just like in our previous examples, that c is our initial condition, if you will, our initial amount. So that's why we change it to p sub 0. Because ultimately it's just a variable, and we use p sub 0 to represent the fact that that's our initial p value here. Now, in terms of this problem, again, we can derive it and use their variables. Really, ultimately, it's the same as that continuous change model that we did with y in t or y in x, whatever the variables are, it doesn't really matter. But bottom line is we get that same exact equation. So knowing that, it says here that the initial condition here is that p equals p sub 0 when h equals 0. That's why we have our c is p sub 0. That just is our initial condition. Now, they also told us that this dp dh here is the pressure. Okay, when we're h above sea level, and the information they gave us here to find some of this stuff is that suppose that the pressure at sea level is 1,013 millibars. So that means that they just gave us one of our variables, which is p sub 0. Our pressure at sea level is 1,013, so that can replace that. So now we have a model that has just two variables in it. Okay. And if we could find k, then we could relate any pressure and any height to one another. So the other information that they told us is that the pressure at an altitude of 20 kilometers is 90 millibars. So if I put in 90 millibars, and I put in a height of 20 kilometers, then the only variable in that sentence is k. So if I divide 90 divided by 1,013, get e to the 20k, and then take the natural log of both sides, and divide, I get natural log of 90 over 1,013 over 20 equals my k. So going back up to this point, my new equation then is 1,013 e to the ln of 90 over 1,013 divided by 20 h. And again, we could give a decimal for this value right here. However, I don't want to give a decimal rounded and then use a rounded answer to make another answer, so I'll just leave it as exact until I'm ready to actually find a final answer here. So I'll just leave that k as is. And ultimately, the question in part B here is based on all that, what's the atmospheric pressure when height's 50? Well, if I plug in my 50 in for h, just calculate a problem. So if we do our 1,013 and our e to the ln 90 divided by 1,013 and just divided by 20, the whole thing. I got my e argument right there. And actually, I'm going to multiply that by 50. I need one more parenthesis up here on this one. I think I got it typed in correctly. Let's find out. Nope, there's in the parentheses somewhere. Let's find out here. That's well, it might need to be. Not need that one. Let's try that. Nope, that's not right either then. Alright, well, let's do it this way then. If I do my natural log of 90 divided by 1,013, just keep these numbers in there. That's divided by 20. So there's my, that part times 50 would be that. And if I go e to that, whoops. I get that, and times 1,013. Oh, that did work out right. Let's see. So ultimately we'd get 2.383. That was right in the first place. Right. And keep in mind this is pressure, so it's in millibars. Make sure we have that on there. Let's think about why that makes sense here in this problem, why that makes common sense. We knew that at sea level the pressure was 1,013. right? When we went up to 20 kilometers above sea level, it was 90, so it got lower, didn't it? So if we go up to 50, it should be even what? Should be even lower, so seems to be reasonable then, doesn't it? 2.38. And then finally it says, at what altitude can will the pressure equal 900? Well, if we put in 900 for pressure, then we're ultimately just going to not 50 this time, we're looking for H this time. So ultimately we'll just solve that sentence. Okay. Put in 900 for pressure, find H. So we divide, and then it's pretty much the same solution as what we did over here, isn't it? Divide by 1013 and then take the natural log of both sides. Divide again to get H by itself. Okay. And I don't know what the answer is off the top of my head, but should be, if it's 900, shouldn't be terribly far off the ground, should it? Remember, it's 1013 at sea level. 900, we won't have to go up too high to get down to 900, will we? We only have to go up to 20 to get down to 90. Right? So it should be a fairly small number. Right. Questions on that one?
Right at the beginning where you're separating the variables,
Mm-hmm.
why did you divide by p? Like, how are you supposed to know that?
Because ultimately that P has to be with the dP,
Because there's,
because they're the same variable.
okay.
So anything with P has to be with P, anything not has to go with the other. Other questions on this one? All right. Let's take a look then next at our multiple choice problems that I asked you to do here. We had some problems regarding position, velocity, and acceleration first here. And the first one, let's check it out, see if we got the correct answers here. It says the car is slowing down in such a way that its acceleration is negative 6t plus 2. It says the car will come to a complete stop at time 3. And it says the velocity of the car at any time is what? Well, ultimately, if we were to get back to ds dt from d squared s dt squared, we need to find the antiderivative. So if I know that my ds squared dt squared is negative 6t plus 2, hopefully, anti-differentiating that, we got to negative 3t squared plus 2t plus c. And if we did so, we can find c by using the initial condition here. Told us the car will come to a complete stop at time 3. That means when time is 3, what's the velocity? That's 0. So if we put our 3 in, we can use that information to solve for c. So we get ultimately negative 27 plus 6 plus c, negative 21 plus c equals 0. So if we added 21, we get 21 equals c. And therefore our final equation then is ds dt equals negative 3t squared plus 2t plus 21. And if you did that correctly, it should have matched up with letter E. Should have gotten letter E for that first problem. Questions on any parts of that one? All right. The next one tells us the position of the particle is given by negative 5t squared, and we want the average velocity for the particle over the time 0 to 3. So again, recognizing that if it's average velocity, we need the change in position over the change in time. That's what average velocity is. Change in position over change in time. We know the change in time is 3 minus 0. Okay. The change in position, we need to find the positions at time 0 and time 3. Well, s of 0 here would be 0. S of 3 here would be negative 45. I put in my 3. 3 squared is 9. 9 times negative 5 is negative 45. So if I do my negative 45 over 0, I get negative 45 over 3 which ultimately gives me negative 15. And so what is my average velocity? Be negative 15. There's no units on this, so we don't have to worry about the unit part, but ultimately, again, all we're looking for is the average velocity, which ultimately is our change in position over change in time. Okay? We don't need to find a derivative here because we're not interested in the instantaneous velocity. We want to know what is the average velocity. Okay? So all that is a slope, and we find our change in position over change in time. Questions on that one? The next one says velocity of a particle on a line is v of t. It's 3t to the 1/2 plus 5t to the 3/2. So that's our velocity. And in this part, it says how many meters did the particle travel between time 0 and time 4? Okay. So how many meters did it travel? Ultimately, it's going to be a matter of finding the total distance traveled. And remember that if I have a velocity curve, keeping in mind that if this is meters per second versus seconds, if I were to draw a picture of this, whatever the picture may look like, it doesn't really matter what kind of curve it is. The area under that curve, if I were to find that area, is going to give me meters per second times seconds, which gives me what? Meters. Okay? So ultimately, we're going to need to integrate here on 0 to 4. Now, we have to be careful, though, because if we integrate this on 0 to 4, if we just do that integral, the question is, does that give us total distance? Maybe. Okay. It would as long as this has all positive values. True? But what if this gave us some kind of negative values? Then that's not going to give us total distance traveled. It's going to give us displacement. Okay. It's going to give us the change in position. And so therefore, if I just do this, okay, it might give me the total distance as long as it has all positive values, it would. But if there's negative values, okay, that's not going to work. Okay, so we have two choices here. We could graph this and see if it does have any negative values, and if it doesn't, then we could just do the integral as is. Okay? If it does have negative values, then we could find where it goes to negative, and we could do two separate. True? Figure out the positive, figure out the negative, make the negative positive, and add them together. Okay? Or what other adjustment could we make to get the total distance here with this integral and not have to do all that? Yeah, if we just did the absolute value, wouldn't that make the negative parts positive and give us total distance traveled? Okay. So if we do that instead, and we do our absolute value of 3x to the 0.5 plus 5x to the 1.5 as our integrand. Type that in there properly. Should get an answer of 80. And again, keep in mind that your calculator doesn't just know the answer to all the integrals. It uses an algorithm to calculate that, so there's some error from time to time. And keep in mind that we could also, this isn't really terribly hard to do by hand. If we did it by hand, we'd get actual 80. And you notice that the choices there, the only choice that even remotely close would be 80. Anything else is not even close, so should be choice D for that one. Questions on that one? Alright, okay, and the next one, let's see what we should have gotten for that one. We have a particle that's moving along a straight line, has a velocity equation this time of e to the t. And the question is, how far does the particle move from time 0 to time 2? Now in this particular case, if I did 0 to 2 of e to t dt, okay, why do I not need the absolute values? E is positive valued on 0 to 2, isn't it? So we can put them, it doesn't hurt to have them there, but ultimately it's positive anyway. So, and just to, we can do this one with the fundamental theorem since we have a simple antiderivative. We do e to the 2, e to the t, and then from 2 to 0, be e to the 2 minus e to the 0. So it'll be e to the 2 minus 1 would be our answer. Should have corresponded to letter A. Questions on that one? Alright, okay, the last three, some more differential equation problems here. They gave us in 3393. Gave us dy dx equals 2y squared. They gave us an initial condition. and they want us to figure out what y is when x equals 2. So ultimately, if we were to separate our variables here, so notice the y stuff went with the y, right? Okay. And if I anti-differentiate y to the negative 2, that's, keep in mind that a lot of people try to do natural log here, but this is not a natural log because it's not y to the 1, it's y to the negative, it's y to the 2, which is just a power function. So if I have y to the negative 2, that would be y to the negative 1 divided by negative 1. So negative y to the negative 1 ultimately here. On this side we have 2x plus c. And once again, at this point, we plug in our initial condition, which our initial condition was negative 1, 1. So if I put in a negative 1 here and a 1 here, I get 2 plus c on this side. Over here, if I go negative 1 to the negative 1, that's the same as 1 over negative 1 to the 1. So that's ultimately negative 1, and so negative negative 1 would be 1. Okay? So ultimately, again, negative 1 to the negative 1 would be 1 over negative 1 to the 1. So it would be 1 over negative 1, which is negative 1. So negative negative 1 is positive 1. So ultimately, subtracting 2, we get negative 1 for our c. And from there, we have negative y to the negative 1. 2x minus 1 is our right side. And at this point, I would get rid of the negative, make it negative 2x plus 1. Solving this for y. Keep in mind that this is 1 over y, negative 2x plus 1 here. If I multiply by y, I'd have 1 on this side, I'd have negative 2x plus 1 times y here, and then I would divide and get 1 over negative 2x plus 1 equals y. So we can get the y by itself as such. And then at this point, they wanted to know y when x equals what? X equals 2. So if I do 2 in there, I get negative 4, and negative 4 plus 1 would be negative 3. So I get negative 1/3 equals y. So that would be my sequence to figure out that one, which ultimately corresponds to letter B you should have had. Questions on any of those steps? Alright, and the next one, we have dy dx equals ky. And it says that y could be, and once again, we could solve this differential equation similar to what we just did a minute ago with that dp dh. Okay, however, we know that the answer has to look like this. True? Because this is that type of differential equation. If dy dx or dy dt or whatever, and actually that's a kx, actually it was a t in the first place, wasn't it? Sorry. So t, not x. So ultimately our y equals y sub 0 e to the kt would be our answer if we were to separate and solve that. And so if you look at the choices that we have there out of our group here, which one has that form? Yeah, the only option here is B, isn't it? Okay. So again, it said that y could be. Okay, ultimately, that constant is going to depend on the initial condition. True? And so, but again, the only one that has the right form is B. So knowing the relationship between this kind of differential equation and this kind of solution, okay, would I have to actually do the separation of variables to get that right on the multiple choice? Nope. However, if you didn't remember that, though, could you do the separation of variables and figure out what y is equal to and compare it to the choices? Sure. Take you a lot of time. It might take you 3-4 minutes to do that, which is a lot of time when you only got 45 to use, right? So, said if you know that, then you can, the problem should take you less than 10 seconds to pick out which one's right. True? All right, and then the last one, we have another dy dt this time equals ky. And it says that if the population doubles every 10 years, we want to find the value of k. So ultimately, once again, I'd immediately go to my general formula here, knowing that that is that type of differential equation. We know the population doubles every 10 years. So ultimately, wouldn't that right there give me means to find k? I'll just consider the population 1, and the final population being 2. That would be a doubling situation. And remember, it doesn't matter what the population is, because even if I knew the population was 10,000, I'd put a 20,000 here, and I'd divide by 10,000 to start the problem, wouldn't I? So ultimately, what would I wind up with no matter what the beginning population is? 2 on this side and 1 on this side. Okay. what's my answer? Natural log of 2 equals 10k. So it'll be natural log of 2 divided by 10 equals k. And if we type that in there, you should have gotten 0.0693, which is actually corresponds with letter A. Questions on that one?